In our previous section, we got an introduction to the basic ideas of probability, and all of our examples were discrete, where we could list discrete and finite. We could list everything in the sample space and find the probabilities by counting, where the probability that an event occurs was the number of successful ways that event could occur divided by the number of possible outcomes, or the number of outcomes in which that event occurs divided by the number of possible outcomes. We're going to add to that some more formulas and ways we can compute probability in a little bit more complicated situations in this section. Okay. So a recap of what we learned in the previous chapter, which is chapter 12 in the book that I'm using right now. So the numbers of these rules aren't important, but they're listed here. So the probabilities that an event occur, they're always between 0 and 1. Okay? You can't have a probability of 2 or -5 or something. The probability is a number between 0 and 1. If you convert to percent, they're between 0 and 100%, where 0, an event cannot occur, up to 100%, an event must occur. The probability of the sample space is 1 because something in the sample space must occur. If A and B are disjoint or mutually exclusive, meaning they cannot occur at the same time, then you can find the probability of A or B just by adding the separate probabilities. We call this the addition rule for disjoint events or mutually exclusive events. And because A and not A are mutually exclusive, either A happens or A doesn't, when we add those we should get 1, so the probability that A does not occur is 1 minus the probability of A. So those are the things that we carry in from the previous chapter. Okay. If we want to start generalizing, especially if we want to do the probability of A or B when they're not mutually exclusive, Venn diagrams will be helpful to see what's going on here. So a Venn diagram, so a mathematician with the last name Venn, use these types of pictures to represent sets, where it doesn't matter what objects you use. Sometimes they're nice perfect circles. Here they're more blobby shapes. But we have two sets, A and B. In this case, they're disjoint, mutually exclusive. They don't intersect. There's no cases where A and B happen at the same time. If they do intersect, the picture would look more like this, where A and B are overlapping, and the intersection would be that part where they overlap. So what happens is when they're disjoint, you can add the probabilities together and there's no overlap, but if you add the probabilities together and they overlap, you're double counting the intersection, and all you have to do is subtract off the probability of the intersection, the probability of A and B. So that gives us the more general rule for addition of two events. The probability of A and B in general, or the probability of A or B in general, is the probability of A plus the probability of B minus the probability of the intersection of A and B. And that formula is always true when they're disjoint. The probability of A and B is 0, and you just get probability of A plus probability of B. Okay, here's an example where I'm going to have to use that formula. Okay, so a class has 30 students, 18 girls and 12 boys. 9 of the girls and 7 of the boys are over 20. If a person is chosen randomly from this class, what's the probability that this person is a girl or over 20? So there's a lot going on in this question here. Okay. So let's convert to words what we're trying to find here. In the last sentence there asks, what's the probability this person is a girl or over 20? So we want to find the probability that the randomly selected person is a girl or over 20. Symbolically, if we apply our formula there, it'd be the probability that the person selected is a girl plus the probability the person selected is over 20 minus the intersection, the probability the person is a girl and over 20. And we have the numbers to compute each of those. Okay. Probability that it's a girl I have is 18 out of 30. Okay, there's 30 students in the class, 18 are girls. Probability that it's over 20, well, let's see, 9 of the girls, 7 of the boys. Add that together, and we're going to get 16 out of 30, or 9 plus 7 over 30. And then minus the intersection, well, that's 9 of the girls that are over 20. A girl and over 20, there's 9 of those. And so we can compute there. We have a common denominator, so go across the numerators. We have 18 plus 16 minus 9 gives us 25 out of 30, which you could reduce if you want to or turn into a decimal. But there's an application of using the general addition rule for the probability of A or B. Okay. And so it'll reduce to 5/6 or 0.83 repeating. So about 83% chance. Here's an example from a standard deck of cards. If you're not familiar with a standard deck of playing cards, just Google it and you can get a picture of the whole deck where you have 2 through 10. You have 4 suits. You've got the diamonds, clubs, spades, hearts. half of them are red, half of them are black. You have 2 through 10. You have the jack, king, queen, ace. So your common deck of cards here. There's 52 playing cards in the deck. So if I select a card randomly from a standard deck of 52 playing cards, what's the probability that the card will be an ace or a heart? Okay. So again, let's start with a verbal and symbolic description here. So we want to find the probability that the card selected is an ace or a heart, which by our formula, we would add them together and subtract the intersection. So the probability that we select an ace plus the probability we select a heart minus the probability we select a card that is an ace and a heart. Okay. Well, if you think about the deck, there's 4 aces, 52 cards, 4 aces, 1 for each suit. So you have 4 out of 52 would be the probability of selecting an ace. For a heart, it's 1/4. You could set it up as 13 cards out of the 52, but a fourth of the card are hearts, a fourth are diamonds, a fourth are spades, a fourth are clubs. So the probability we select the heart is going to be 1/2, or in a common denominator, 13 out of 52. The probability we select an ace and a heart, there's only one of those, the ace of hearts, so minus 1 out of 52. And so you have the common denominator, compute that up, and we get 16 out of 52, which reduces to 4/13, or 0.3077, which I probably rounded there.